Hello everyone. This is part 3 of the single degrees of freedom damped vibratory system. If you have not watched part 1 and part 2 of this video, I highly recommend that you go back and watch part 1 and part 2 of the video. In part 1 of the video, I have derived the governing differential equation, and in part 2, I have solved the governing differential equation. In this video, we are going to understand what is a critically damped system, what is an overdamped system, what is an underdamped system. So to begin with, let me first write the governing differential equation of the single degrees of freedom damped vibratory system. It's a free vibration. So first we have the inertia force m into d square x over dt square. And we have the damping force, which is given by the expression c into dx over dt. And we have the spring force, which is k spring constant into displacement. And the sum of all the forces should be equal to 0. You can easily get this expression by using Newton's third law, that is, the action force should be equal to the reaction force. Okay, I'm going to write the solution to the governing differential equation. As I said in part 2 of the video, I have derived the solution for the governing differential equation. The solution to this particular governing differential equation, which is the displacement of the mass at any instant of time. You can see the mass here, and if you solve the governing differential equation, you can tell what is the displacement of the mass at any instant of time. And that is given by the expression x of t is equal to a1 into e power lambda 1t, and we now know what is the value of lambda 1 minus psi plus root of psi square minus 1 into omega n into t. Now, when it comes to this particular notation, sometimes I am calling that as psi, sometimes I am calling that as eta. Please forgive me. So I am using the words psi and eta interchangeably. Okay. And you know that if you have two solutions to this particular governing differential equation, you can add the two solutions, which is also the solution to the governing differential equation. So the second solution is plus a2 into e raised to the power minus psi minus square root of psi square or eta square minus 1 into omega n into t. Okay. Now clearly you know what is psi. Psi or eta, that is damping factor, which is damping coefficient to the critical damping coefficient, which is the ratio of the damping coefficient to the critical damping coefficient. Critical damping coefficient psi suffix c is 2m omega n. Okay. So m is the mass, omega n is the natural frequency, and c is the damping coefficient, which is the ratio of the damping force to the velocity. Okay. Now, this expression is of the form e power a plus b. Now, if there is an equation of the form e power a plus b, you can write that equation as e power a into e power b. That is what I'm going to do in the next step. So let me continue. This expression can be written as x of t is equal to a1 e power a plus b can be written as e power a, which is minus psi omega n into t, or minus eta omega n into t, into e power, it's a into, fine, e power square root of eta square minus 1 into omega n into t. So e power ab can be written as e power a into e power a plus b can be written as e power a into e power b. Okay. The same trick here, plus a2 This is of the form e power a plus b or e power a minus b. Of course, this is of the form e power a minus b. That can be written as e power a into e power minus b. Okay, it is e power minus psi or eta into omega n into t into e power minus square root of eta square minus 1 into omega n into t. That's right. Now, in this expression, you can see that e power minus psi omega nt comes here, and the e power minus psi omega nt is also appearing here. You can take this red box outside of the equation. So I can write this equation as x of t, and write that as e power minus psi omega n into t. That can be taken outside into a1 into e power square root of eta square minus 1 into omega n into t plus a2 into e raised to the power minus square root of eta square minus 1 into omega n into t. So I'm taking the common terms outside. So okay, so far we have just mathematically arranged the equations. Now, what happens in the case of a vibration where the damping factor is equal to 1? Now, what do you think is going to happen to this equation when the damping factor is equal to 1? So this is going to be the case 1. So in case 1, we are going to say the damping factor, which is the ratio of C to the CC, what happens if that becomes 1? How do you think the system is going to behave? We are going to simulate this equation in MATLAB, and we are going to understand how the system would behave when the damping factor is equal to 1, when the damping factor is less than 1, and when the damping factor is greater than 1. Now, when the damping factor psi is equal to 1, if you are putting psi is equal to 1 in this equation, you see the power, it becomes 0. If you are putting psi or eta equal to 1, then it actually becomes 0. So anything to the power 0 is actually 1. So the expression reduces to the form x of t is equal to e raised to the power minus, now eta is equal to 1, so it becomes minus omega n into t into a1, anything power 0 is 1, plus a2 into anything power 0 is 1. So you are getting sum of two constants. You can see sum of two constant is again a constant. Maybe I can call this as d, a bigger constant. So finally, the equation when the damping factor becomes 1 is x of t is equal to capital D into e raised to the power minus omega n into t. That is the solution for a critically damped system. So I have to say this is the solution to the critically damped system. The reason why I'm calling this as a critically damped system is because the damping factor is equal to 1. And you see, watch it very carefully at this particular equation. X is the displacement of the mass as a function of time, and a d is a constant. It's just a constant. And how do you think the constant, the amplitude, is going to decay over the period of time? Well, the amplitude is going to exponentially decay over the period of time. So this equation is going to be of the form d into e raised to the power minus omega n into t if you take the amplitude along the y-axis, I mean the displacement of the mass along the y-axis, and the time is plotted along the x-axis, you are going to get an exponentially decaying system. So this is case 1 when the damping is critical. Now let us see what would happen if the damping is not critical, but when the damping factor is going to be less than 1, what is going to happen to this expression. So I'm going to write the expression again. So here we go. Let us go to case 2. So in case 2, what happens when the value of the damping factor becomes less than 1? Let me write the expression now. X of t, the expression that we have got, you can see that it is e raised to the power minus eta omega n into t into a1 into e power minus square root of eta square minus 1. I'm sorry, it's plus, right? It's plus into omega n into t plus a2 into e raised to the power minus square root of eta square minus 1 into omega n into t. Okay, now this particular expression is an expression that holds good perfectly well when the value of eta is greater than 1. That is, this is an expression that holds perfectly well for an overdamped system. You don't have to modify anything in this expression. Once you know the values of a1 and a2 after applying the boundary conditions, you can see that the value of eta is greater than 1. That is an overdamped system. We are going to simulate in MATLAB and see how an overdamped system is going to behave. But what happens when the value of eta becomes less than 1? To this expression, what is going to happen when the value of eta becomes less than 1? You see, when the value of eta becomes less than 1, it becomes less than 1. The square of a digit that is less than 1 is going to be smaller than 1. So inside this term, you are going to get a negative term. Okay? So what we do is you are going to get the negative sign outside this expression. So that's what we are going to do in the next step. It is x of t is equal to e raised to the power minus eta omega n into t into a1 into e raised to the power. You see, I can write this expression as root of 1 minus eta square, taking the negative sign outside, which means that you will be taking root of minus 1 outside. And what is square root of minus 1? And the square root of minus 1 is I. And we have a very good reason to do this. And the reason is because the eta damping factor is going to be less than 1 into omega n into t, the same here, plus a2 into e raised to the power minus I into square root of 1 minus eta square into omega n into t. Okay, that is our expression. Now, to simplify this expression even further, I am going to use something called as introduce a notation which is called as omega d, and let omega d is root of 1 minus eta square into omega n, where omega d is called the damped frequency, because obviously this frequency is going to the damped system, okay, this damped spring mass system, this is our damped spring mass system, it's going to oscillate at this particular frequency. And you can see obviously that when the value of eta becomes less than 1, then obviously the damped frequency is going to be less than the natural frequency. So you are actually going to get a very sluggish movement in the case of a damped vibrator system. Okay. Now, if you introduce omega d as root of 1 minus I square into omega n, then you can rewrite this expression as, and remember, what is omega d? It is the damped frequency, right? It is the frequency at which the damped vibratory system is going to oscillate. The single degrees of freedom damped vibratory system is going to oscillate. Okay, it's obviously because it is of the form e power omega. If you know, this entire expression is of the form e power omega t, where omega should be the frequency. Now this time it's damped frequency, so this entire equation is of the form e power omega t, right? That's right. So in the next step, I can rewrite this expression as x of t is equal to e raised to the power minus eta omega nt into a1 into e raised to the power, okay, this is of the form I into omega d into t, right? Because square root of 1 minus eta square is omega d, plus a2 into e raised to the power minus I into omega d into t. That's right. And you know what is e power I theta? E power I theta is cos theta plus I sin theta. We are just going to expand e power I omega d t in this particular form, so that you are actually going to get x of t is equal to e raised to the power minus eta omega nt into a1 into, what is e power I theta? It is of the form e power I theta, and that is cos theta. In place of theta we have omega dt plus I sin omega dt. That's right, that's right. Plus a2 into cos theta. Now this theta is minus omega dt, cos theta minus I sin theta. Okay, right? It's cos omega dt minus I sin omega dt. That's right. In the next step, we are going to assemble the cos terms common and the sin terms common in the next step. So if you take the cos terms common outside, it will be of the form a1 plus a2 into cos omega dt. If you take the sin terms common outside, it will be of the form a1i minus a2i into sin omega dt. Okay, so that's what I'm going to do in the next step. So let me take the cos terms and the sin terms common outside. So x of t is equal to e raised to the power minus eta omega nt into the sine terms common outside. I have to take the sine terms common outside. If I take the sine term common outside for these two terms, it will be of the form, okay, I'm taking the cos terms common outside. It is going to be of the form a1 plus a2 into cos omega dt. So it is going to be of the form a1 plus a2 into cos omega dt. And for the next terms, if I take the sin omega dt common outside, so it is going to be of the form a1i minus a2i, that I can be taken outside, into sin omega dt. Now I'm going to call this term as one constant. Let me say it is capital A, and I'm going to call these terms as another constant. Let us say it is capital B. Now what happens to the expression? X of t is equal to e raised to the power minus eta omega nt. Okay, this is a cos omega dt plus b sin omega dt. And in the next step, what I'm going to do is I'm going to call, this is a number. It can be any number. And this is a complex number. But anyway, it's still a number. Any number can be written as a product of two numbers, which is x into sine phi. Okay. Now, there is no magic here. There should not be any confusion here. You can write 5 and say any other number 16 as product of two numbers, x sine phi, where x is one number and sine phi is one number. And even this one can be written as a product of two numbers, x into cos phi. It holds perfectly well. Okay. So the number, any number can be written as product of two numbers. In our case, what we are doing is we are saying that the first number is a product of x and a sine phi, and the second number is a product of x and a cos phi. It works perfectly fine. I'm going to tell what is x in a moment. It's very simple to find out the value of x. So in our case, it is x into cos phi. Okay. You can test it out. You can easily find what is the value of x. If you just sum these two, you can say sum and square these two. Okay, square of the sums, x square sine squared phi plus x square cos squared phi is equal to phi square plus 16 square. That's right. So it's going to be equal to phi square because the sum of the first number square plus the second number square. And if you take x squared, pull x squared common outside, you will be getting sine squared plus cos squared phi, that is equal to 1. So x squared is equal to phi square plus 16 square. Now all you have to do is find the value of x, and the value of x is square root of 5 square plus 16 square. Now we have got the value of x. You can easily find the value of phi. How do you find the value of phi once you know the value of x? Well, phi, x sine phi, once you know this value, then you can easily find phi, right? Yeah. So there is no confusion. You can check yourself and it works perfectly fine if you just substitute the values and check yourself whether it works. If you want to check, please check. It works really well. So any number can be written as product of two numbers, which is x and sine phi. The second number can be written as again the product of two numbers, which is x and a cos phi. The trick how it works is because the x depends, the number x depends on both a and b. That's how it works. Okay, simple as that. So if that is the case, so remember that if that is the case, so let me go back and continue this derivation. X of t is equal to e power minus eta omega nt, and this is x sine phi into cos omega dt plus this is going to be x cos phi into sine omega dt. You can pull x common outside, so it can be written as x, capital X into minus e power minus eta omega nt. I'm using the words eta and the sine interchangeably, so it's a bit annoying even for me, so please forgive me. So it's of the forms sine a cos b plus cos a sine b, or sine a cos b plus cos a sine b, or cos a sine b plus sine a cos b. Okay, so this is of that form, so that is sine a plus b. So I can say it is sine omega d t plus phi. So this is of the form sine a plus b. Okay, so sine a plus b is sine a, which is sine omega dt, into cos b, which is cos phi, plus cos a into sine b. Now what is the interpretation? Here x is the amplitude, and if you forget this e power minus psi omega nt for a minute, If you just assume that e power minus psi omega nt doesn't exist, just imagine, just to mathematically interpret this equation, if that is not existing, then the amplitude is just going to vary in a sinusoidal fashion like this. There is absolutely no problem. Now, what do you think is going to happen when you hit the sine wave with an exponentially decaying term? When you hit a sine wave with an exponentially decaying term, then the sine wave is also going to decay exponentially like this, right? So you can imagine that the e power minus psi omega nt is not there. It's a perfect sine wave with an amplitude x. Okay, that's our amplitude. But if you hit it with an exponentially decaying term, then the decaying term, when it hits the sine wave, it makes the sine wave exponentially decay. So that's the interpretation. Now, shall we do the analysis in MATLAB? We're going to do the analysis in MATLAB. I have built the equations for the three cases. So what are the three cases? The first one, it's overdamped. So here is our equation for overdamped. So I can put the highlighter. So, okay, this is our equation for an overdamped system. Everything is perfectly fine for an overdamped system, right? When the value of damping factor is greater than 1, right? So that was our overdamped system. What is the expression for critically damped system? So here is our critically damped system. I told you that in the case of critically damped system, your response, displacement of the mass decays exponentially. In the case of an underdamped system, right, it's going to be a sinusoidal form, but the sinusoidal wave is being hit by an exponentially decaying term. So the sinusoidal wave is going to exponentially decay. So here is the MATLAB simulation result. This is the response for an overdamped system. Sorry about the terrible handwriting. And this is the response for a critically damped system. That is when the value of eta is equal to 1, when the damping factor is equal to 1. Here the damping factor is greater than 1. Now obviously you can see that when the damping factor is equal to 1, the system, the mass comes back to the equilibrium position at the shortest time, right? In the case of a system where the damping factor is going to be less than 1, then it's going to be a sinusoidal decay term, something like this. So this happens when the value of eta is less than 1. So critically damped system makes the mass go back to the equilibrium position in the shortest span of time. Where do you find such an application? Well, you find such an application in guns where the recoiling should happen in the shortest time duration possible. Okay, there should not be any oscillations there. Okay, here we have MATLAB simulations of the same expressions. I have built that.